Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 17, 2025, about 2 weeks ago. This paper turns text-to-image diffusion models into task-adaptive visual encoders for robotic control without fine-tuning, using learnable task prompts and frame-level visual prompts, and it reaches state-of-the-art results. Deep mind control mean 74.3, meta-world success 95.2, and adroit success 65.3. The paper is titled, Exploring Conditions for Diffusion Models in Robotic Control. And as we'll see later, the implications for control policy training are quite significant. Figure 1 shows how conditioning a text-to-image diffusion model changes control performance. Conditioning means adding signals that steer the model's visual features toward a task, so the policy receives more relevant cues. On the left, the pipeline takes an observation, passes through the diffusion model, and outputs an action. The center contrasts three conditions, from a null prompt to text prompts to learn task and visual prompts. On the right, bars indicate stronger results for the learned prompts. MetaWorld reaches about 96. Deep Mind Control reaches about 74. Adroit reaches about 65. Well, Figure 1 showed the high-level pipeline and gains. Figure 2 shows why conditioning matters. The left panel depicts a task-agnostic encoder that feeds the same frozen features to every task, which leads to uneven control. The right panel adds conditions, so the diffusion model produces task-adaptive features. Those conditions include short learnable task prompts and dense frame-specific visual prompts, so attention focuses on the hand or the object that matters for the current goal. Alright, Figure 4 explains how the method turns frame observations into action by conditioning a diffusion model with prompts. Learnable prompts mean small vectors that the policy can adjust, so the visual encoder pays attention to the right regions. The top row illustrates visual prompts from a frozen vision encoder combined with task prompts. The bottom block shows early diffusion layers using cross-attention to produce a visual representation which the policy maps to control actions. So, Table 2 reports success rates on MetaWorld and shows the approach leads the pack. The mean success reaches about 95%, which tops both task-agnostic and text-conditioned baselines. Scores are high and steady across assembly, bin picking, button press, drawer open, and hammer, because learnable task prompts and frame-level visual prompts adapt to each scene. Results average over 3 seeds, so the comparison reflects stable gains rather than lucky runs. So, while Table 2 highlighted MetaWorld success, Table 1 reports Deep Mind Control normalized scores, indicating the method leads overall. The mean column places the approach at about 74, which exceeds every baseline by a comfortable margin. The ORCA row also shows balanced gains across walker stand, walker walk, reacher easy, cheetah run, and finger spin. Text prompts vary widely, so caption text sometimes helps, but also drops cheetah run. Wrapping up, 2 takeaways stand out. Textual conditioning alone is unreliable for control because the domain gap breaks grounding, and learnable task prompts plus frame-level visual prompts reliably adapt frozen diffusion features, driving strong gains across benchmarks. The broader implication is clear. Conditioning design can turn generative encoders into robust control backbones. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.